Can people hear me? Okay. So I'm James Rhodes, and this is our cast of several who have helped pull this splinter session together. So Meenak Singha, Sangeeta Kumar, Sangeeta Malhotra, and Isaac Wald sitting over there will be the folks presenting, plus Austin Gabriel Pillai, who had his iPoster ending 90 seconds ago, so he will presumably get in here in a few minutes' time. And without further ado, I'll hand it off to Sangeeta Malhotra to get us going. We should be on Zoom. We are trying to record the session, and yeah, I think that's about all I wanted to say right now.
So, is anybody on Zoom?
Yes,
Can you see people?
there are 3 folks.
Hello, welcome to this session. We are very excited about Roman launching soon. And thanks to all the hard work of some of the people here. This is supposed to be designed to be for introduction to spectroscopy, a gentle introduction. How many of you have worked with slitless spectroscopy data? I think you should leave the room. No, just, okay. We will settle for do not throw tomatoes, okay? Or at least not rotten ones, okay? So you might find this too simple for you, but hey, we are trying to get, what are we doing? Okay, let's start with, what is the aim of this data challenge? The aim of this data challenge is introduce Roman spectroscopic elements, get familiarity with slitless spectroscopy, exercise some codes, and build community so that, you know, we'll learn and do things together. Unfortunately, some of our friends from West Coast are missing because of all the things that happened around Pasadena. So we give grace to one another. We also have one of our team members missing, family things. So there'll be some gaps. Hey, Austin. So we're trying to build community here, and we give grace to each other. Those are the rules here. So not rules, guidelines. So what is slitless spectroscopy? I think sometime I said something about unholy amalgamation of space and wavelength, and that was not popular. So I'm saying it again. Isaac will speak more to it. This is a thing I've stolen from him. I'm just going to introduce the challenge to you. So what's the sort of data flow for dealing with slitless spectroscopy? You have a busy astronomical scene, as you saw in the previous slide. And from that, you extract 2D spectra of individual objects, and then you extract 1D spectra of individual objects, and then you identify what are these things, okay? What redshift, what is the nature of the object, etc. But the data challenge flow will go in reverse because we don't want to scare you in the first instance. Not that it's scary. So we'll start by dealing with 1D spectra. And the next session of data challenge, which we expect will be the next AAS and remote, we'll talk about going from 2D to 1D. And then in the last one, we'll talk about going from a busy astronomical scene to individual spectra. And so it goes up in difficulty. So yeah, this is what I just said. So let me just say, what's the agenda for today? This was my vapid talk. They keep me around for comedy, such is my life. And then Isaac Wald will give the right content, the real talk. Austin will talk about espresso simulations. James will give a Prism introduction instead of Tree, who's couldn't make it. And then we'll start on some hands-on work. So if you haven't registered and gotten all your instructions on how to join the Jupyter notebook and all, come in. It's it's good to sit down and, yeah. So there'll be some hands-on exercises at the end. And, oh, sorry, next slide has all of these, how to access the data challenge. This was so rapid that I don't think you have questions, but if you have questions, I'm here. No, yay. So on to,
Let's leave that up for 20 seconds more. If you did register, you hopefully have an email that has that information in it. And you may have gotten one recently if you registered since last night. So I will switch windows.
Thanks, James. Okay, so I'll be giving a very hopefully gentle introduction to slitless spectroscopy, and I'll be focusing on Roman's slitless spectroscopic capabilities. So on this title slide, I'm showing Roman's detector array, so 18 different detectors, a total field of view of about 0.3 square degrees, and then in the center here, I'm showing a single detector's worth of a simulated extragalactic field of Roman's Grism, showing just a single detector's field of view. This is from Austin's espresso code. So to begin with, I thought I would give just one slide's worth of content towards just emphasizing the importance of spectroscopic observations overall. So, spectroscopy is one of the primary tools in which astronomers are able to study the physical properties of the stuff that we're interested in, so planets, stars, nebulae, and galaxies. And here I'm just showing one exciting near-infrared spectra. This is a press release from James Webb. And, this was exciting because you can see here in the inset over here, this very faint compact galaxy that when we study its near-infrared spectra, we are able to obtain a wealth of information. So this is an object at a redshift of 8.5. And through these emission lines, we can constrain things like the metallicity through the oxygen line ratios, the dust content through the hydrogen line ratios. The oxygen doublet allows us to constrain the gas density, and the amount that the lines are redshifted along with the standard cosmology gives us a distance, which is far more accurate than we would be able to obtain with photometry alone. So this is, an example of some of the exciting things that we can obtain with near-infrared spectra. And before I go into slitless spectroscopy, I thought I would talk about how this object was observed through James Webb, because perhaps we are more familiar with slit spectroscopy or multiple object spectroscopy. And so here's my cartoon version of how this observation, these multi-slit observations are conducted. So on the far left, I'm showing a broadband image, and when you set up your slit mask, you isolate the objects that you're interested in. You design a slit mask so that only the light from the objects that you're interested in pass through your slit mask and are dispersed onto the detector, which I'm depicting on the far right. And so here on the detector, you can see depicted 2D spectra that are nicely, falsely color-coded so that you can see where the blue and red wavelengths are. And you can imagine that we might find multiple different types of objects. So here is an object that has these dark bands. When you collapse it into 1D, you see this nice absorption line spectra. Here's another example of a type of spectrum. This is emission line galaxy, and you can see its corresponding 1D spectra once it's collapsed. So this is this emission line galaxy is analogous to this James Webb example that I was showing earlier. But this is not an intro to slit spectroscopy. It's an intro to slitless spectroscopy. So what happens when we remove this slit mask? So, when we do this, all of the objects within the field of view, so here the purple image here is showing a broadband image of all the objects that are within the field of view of this detector. And on the right is showing that all of the objects have their light dispersed across the detector. So there's advantages and disadvantages to doing this. So one advantage is that all sources become a spectrum. So this has massive multiplexing capability. Thousands of galaxies will be able to be observed all at one time in the case of Roman. Additionally, because we're not designing the slit mask, there's no continuum pre-selection. Often when you're designing a slit mask, you are imposing some sort of broadband detection limit. And it means that you can potentially miss strong emission line galaxies that could be detected in the slitless observations. Another advantage is the potential cost and space savings of an all-in-one imager plus spectrograph. So in the case of Roman, when we want to switch from the wide field imager from going from an imaging mode to a spectroscopic mode, we just need to rotate the filter wheel. Also, there's no built-in slit losses. The price that we pay for this is that the spectral resolution is now set by the spatial extent of the objects and the instrument resolution. The other disadvantages is that the sky background now falls on all of the detector, and we can have overlapping spectra. So sources that are next to each other that are in line with each other in the dispersion direction will have their spectra overlap. So the ways in which we can mitigate these disadvantages is that we can go to space and observe in the near infrared where the background is low. And we can also observe in multiple position angles, and this can give us additional information that can help us to disentangle overlapping spectra. So we are specifically interested in the Roman Space Telescope. So this is a Hubble class telescope with imaging and slitless spectroscopic capabilities. The spectroscopic capabilities go from 0.75 to 1.93 microns. And it has this enormous field of view shown here in comparison to Hubble and James Webb. So this is approximately 100 times Hubble's field of view. This is a space telescope, so we are above Earth's atmosphere. We'll be able to avoid all of these bright skylines that are in the near infrared. And Roman has two of these slitless spectroscopic capabilities. And so here I'm showing the response functions for these two slitless elements along with all the broadband imaging filters. So you can see here, the Grism is labeled G150 and the Prism is shown by this other dashed line that's up above. So in general, the Prism has higher throughput. The Grism can go to longer wavelengths, and the Grism has higher spectral resolution. So this slide is showing the Grism and the Prism, the elements that are inserted into the filter element. And the table kind of summarizes these advantages and disadvantages of the Grism versus Prism. So in general, and this is the case in this table, and in general, the advantage of a Grism over a Prism is that, a Grism is a diffraction grating combined with a Prism. And by combining these two elements together, you can generally achieve higher spectral resolution, a more uniform wavelength dispersion. So if you look at Roman's Grism, the wavelength dispersion is about 11 angstroms, whether you're at the blue end or the red end of the spectrum, as opposed to the Prism, where it is more like 20 angstroms at the blue end and 90 angstroms at the red end. And the one drawback of the Grism is that because you're employing a diffraction grating, you will have off orders, spectral off orders, in addition to your science order that you're interested in. And the Grism generally has a lower throughput. So here, again, I'm just showing the throughput curves along with the filter wheel in Grism, or not in Grism, in the wide field instrument. So, the Prism and Grism are just one element or two elements within this filter wheel. And when we want to switch from an imaging mode to a spectroscopic mode, we can just rotate the filter wheel. Okay. So the final thing that I wanted to talk about was how we can use multiple position angles in order to help us disentangle overlapping spectra. So to do this, I'm going back to Austin's simulations. So this is for a single detector of Roman. So this is showing, this is the broadband image again and the slitless image. And we can gain some insight by overlapping these two objects, these two images, and making them transparent to help us identify which objects are producing which spectra. So let's see if this laser works. Okay. So here you can see this bright star is producing this spectra. And then you can see this group of objects that all are producing these spectral group here. And you can see that they all kind of overlap with each other. And for the purpose of the next few slides, I'd like to focus on these two objects here. So this looks like, to me, like a bright star potentially in an extended galaxy. I've aligned these images by eye, so the alignment's not perfect, but you can see here, two objects that appear to have overlapping spectra. However, this is just for this position angle, a position angle of 0. So if we then were to observe the same field of view, but at a different position angle, you can see that these two objects no longer overlap in the same way. And so by observing the same field with multiple position angles, we can gain more information, and this helps us to disentangle overlapping spectra. There's many different reduction programs that have been developed to help disentangle overlapping spectra. Here I'm listing 5, including my own work in 2024, where we investigated the potential for a deep Roman Grism field to study Lyman alpha emitters during the epoch of reionization. Okay, so in summary, spectroscopy is very important for the study of the things that we're interested in. And, so Roman's slitless spectroscopy has exceptional multiplexing capability at the expense of a more complicated background with overlapping sources. We can mitigate some of these problems by, observing in the near infrared where there's a low background, and also by observing in multiple position angles. And so this near infrared spectral capability is essential for the core surveys that Roman plans to take, and also will offer many exciting guest programs. So I'll take any questions. Yes.
The alignment of the spectra and the images.
Mhm.
Do you do it actually in 2D, or do you do it in catalog space, or how is that done?
So in this slide, are you talking about, or if I were to do this in a, so this was just done for the slideshow. So I've just done this. Yeah, but if you're to do this for real, you want to have you want to have a good mapping between the sky position. So given a sky position and a wavelength, you want to have the instrument calibrated so that you know exactly where on the detector you should find that light. And so that is how we've in the past done this, was with optical models where we have that mapping where we can go from sky and wavelength to detector position. Yeah, so sky, RA deck, yeah, and wavelength into detector position. So we were, this is something that the optical engineers were leading. Yeah. Yes. So I am not entirely sure about the way in which Roman, so I think the Roman pipeline will be primarily based on what they're doing for Euclid. And so I think there will be some effort to use the information from multiple position angles. I don't know if it will necessarily be optimized for multiple position angles.
And I'll speak to that. It's Patrick Warren from the SLC. So the spectroscopic pipeline is going to be, the 1D part of it is going to be based off of the 2D part is being developed at IPAC. And that is going to be different stations. So that actually is being developed right now. It will be provided to the community when the spectroscopic data is that actually the TV and the actually be part of the product. Yeah.
Thanks for helping me out.
Other questions for Isaac?
Yes.
The broad wavelength range, do any of all of these also handle the wavelength dependent PSF activities or this one? How do you handle it?
So right now, so I can speak to my work most directly. So right now, my work does not incorporate the PSF differences. So that's something that, you know, in the past, we've been able to kind of skirt around because the wavelength range wasn't a full micron, but here we have a full micron and you do expect the PSF to change from, you know, 1 micron to 2 micron. And so this is a complication that we have not yet incorporated into my own work, but it is something that we plan to incorporate into the next iteration of Espresso, which Austin will be talking about in the next talk. Yes.
The simulation tool, the output didn't match the format of the expected spectral product.
So I'm not involved in developing the Roman's pipeline, so I can't speak to that. Is that what you're asking?
Plans to match with what later on. I'm just wondering because of they're simple pairs, you can convert them to whatever format you want. Okay, thank you.
Any questions online? I think I'm ready. Okay.
On online. So wrong for that. I had that. Would you mind repeating that question? So you're just
Oh, sorry. We have a live microphone. I'll get the microphone for the next session. We'll pass it around for people to ask questions. Sorry about that.
Manage the slide swap and then hand over to Austin. Let's see.
Okay. So thank you all for coming today, and thank you, Isaac, for setting up the stage for me to start talking about Espresso, which is our simulation code for developing high fidelity, realistic Grism simulations for a Roman Space Telescope. And so just to kind of start off the big picture is like, I like to show this specific slide showcasing how powerful Roman is going to be. So in blue is the Hubble Ultra Deep Field, the survey footprint for that. In the white is a larger Hubble survey area. And then you can see in orange, the iconic Roman footprint, the Roman smile, as we call it, right? And you could see that with just one Roman pointing, we'd be able to cover this entire Hubble survey area it would just once, and thus we could thus have great capability for doing a Roman deep field. And so we could do this with broadband imaging, and then we could also do this with slitless spectroscopy. And now to kind of, again, graze over what slitless spectroscopy is, it's when you are dispersing the spectra of all objects within your field of view with no pre-selection or biasing. And so we're able to do this with a Grism, which is a combination of a diffraction grating and a prism, hence Grism. And as Isaac has said, it is a great tool for identifying mission-length galaxies, as well as high redshift galaxies and their features. But con, and again, as Isaac has mentioned, in this very crowded scene, sources can contaminate other sources. And so in this image example over here, we're looking at an HST image on top, a broadband image, and the bottom is using the HST ACS Grism. And then you could see that bright star that's kind of just streaking straight through is contaminating the background galaxies over there. You have a bright broadband galaxy as well that's also doing the same thing. But there are mitigation strategies that we can take care of. And so our goal for the project is that, Roman's going to be launching relatively soon. The years pass by ever so quickly now. And we need to be ready for the large data volume that we will be handling regarding these 18 4K by 4K detectors. And so for the purpose of this work, we wanted to create a realistic mock Roman Grism foreground simulation with multiple optical distortions. Thus, we can provide these data products to the community to thus develop spectral reduction code. And so this is where we've created SPRESSO, which stands for Extragalactic Spectroscopic Roman Emulator and Simulator of Synthetic Objects, lovingly named after the beverage that got me through making this software. And so the simulation consists of 3 parts. In that one, it creates a image data cube of X, Y, and wavelength. This data cube is then used in our Grism simulation pipeline, and then we can utilize all the aforementioned to do custom source injection, where if you want to inject objects of your choosing into our simulated field. Our code base is in Python, and then we utilize libraries such as Numba and multiprocessing to speed up our simulation so that they can be done in a relatively fast time. So here is the example of our pipeline. Again, we'll be covering the data cube generator, the detector simulator, and the source injector through the rest of this talk to basically produce our simulation set. So first, oh, yeah. It's a fun diagram. Here we go. Okay. So let's start talking about inputs. We are using high resolution HST imaging in our simulations. Specifically, we are using the Cosmos field from the Candle survey at a resolution of 0.03 arc seconds per pixel. We have taken the field, have taken a kata out of it, giving us the one that you see over here, which can span about 1.5 Roman detectors. And specifically, this is a combination of both a wide and deep image of what we have available to us. So this is, again, highlighting why we need realistic simulations to thus then produce a full Roman detector arrays worth of data and whatnot. Alongside this image is a segmentation map where you're able to extract the specific objects in your field, including their morphologies, which then gives us 25,000 objects that we are able to throw into our simulations. And these objects span out to even like Redshift 6 based off of the photometric codes that have been used. We are also using an SED library for all of these objects. Specifically, we're using the one that came with the 3D HST survey, which are easy-based, where the original work fit 44 filter profiles to these 7 templates shown before. The great thing about these templates is that they do have a number of emission and absorption features, which includes H-alpha, O2, O3. A con, though, is that there are no stellar templates. However, this is something that we have fixed in post-processing. And so what we've done for this work is we've taken each SED for our galaxies, pre-processed them to fit within the 1 to 1.93 micron range that is Roman's viewing capability in the Grism at a wavelength step of 1 angstrom. Next, as our input is that we take our SEDs and we take our observational image, and thus we then create an image data cube as a function of sky position and wavelength. And so what we do is that using the segmentation map, we extract each object from your image. You're able to find each pixel's contribution, relative contribution to the overall flux, and then you then sample your SED at whatever wavelength to thus then say, hey, this is what the expected overall image will look like at that wavelength. And this is kind of what is being shown in this GIF over here, where as this passes this emission line feature, you see that the entire galaxy brightens up. It's a relatively simple approximation, but it's one that we are using for this first step for this for this work. This process is parallel, so each CPU is working on a specific wavelength slice as a function of time, and then each slice is then saved via sparse compression. So that way you're only saving the pixels that you care about, which gives us a 90% data reduction, and thus makes it a lot more manageable to house on a cluster environment. And so now we're getting into the meat of it being the Grism simulations. I'm going to be talking about some of the features that we've added and modeled in this work. And so each detector has a specific sky to detector polynomial transform. So you have sky position of wavelength, and it tells you where it'll land on the detector of your choosing. Note that each detector is unique, so you can't use the third detector's polynomial to figure out where that light lands onto the fifth detector. We're modeling 3 orders in this work specifically the in-focused 1-1 science order, as well as the 0-0 and 2-2 off orders, which you could see to the left here. We've also added a wavelength-dependent response function for all of our orders, which includes red and blue edge cutoffs, as well as a field-dependent response, which basically says your detector will thus vary basically where on the detector your light lands on. And so to kind of, again, showcase, the full quote unquote picture is that here's a 4K by 4K simulation, a whole chip with all of the orders and optical distortions that I've mentioned. And so we produce noiseless foreground scenes, such as the one over here. So this is everything. There's no removing of objects whatsoever. And as Isaac has mentioned, we're currently using the Hubble PSO. And to kind of highlight, how dense and data rich this field is. Here's our 4K by 4K image, right? And let's zoom in to a 1K by 1K region, which is akin to, again, Hubble's detector size for wide field camera 3, right? And let's just zoom in another level, right? So we're going into 250 pixels by 250 pixels, and you can start to see emission line features. You could see various other distortions, such as the out of focus, the in focus off orders. Another thing is position-based transforms. There should be a video. Oh, not gonna work. Oh, that's a bummer. Okay. Regardless, Isaac showed us what the position-based transforms look like. And basically, we can define a position angle in our simulation file, which then rotates your input image and thus then projects it back onto the detector array. We also have dithering capabilities, so you do X, Y, plus minus dithers, so you can ever so shift the viewing angle with that as well. And then going back, I seem to have lost. But it's not responding anymore. Technical difficulties, ever so present. Here we go. Last feature is source injection, right? So as I've mentioned, we have this pipeline, and so we're able to utilize it to its best capability in being able to, 1, simulate individual objects and thus then add them into our field of view. And so given an input of a science image and your SCD, optionally a segmentation map, you could specify how many of these objects you want to be injecting into your field of view. And this creates a blank template, which then populates it randomly, and then you can then put it through the full pipeline and then take this and then co-add it to our noiseless foreground scenes. It's just a very simple linear combination, right? And these data products are, again, the ones that I've mentioned before. And so here we have an example of a broadband star and mission line galaxy that you can thus inject into our simulations. And so this could be anything that you're of interest with. It could be, for example, a galaxy with a strong AGN feature. It could be a number of broadband stars. If there's something that you want to simulate and see what Roman will be able to do, we are able to do it as long as you have an image and an SED that we can use. And so just to kind of give you a final scope of our simulation, this is, again, a full output using the image that I showcased in the beginning. where you have the full chip in the middle, and then you also then have the edges that are now being simulated through the cropping that's done. And again, it'd be great to thus then have a wide and deep image that can thus do even like half of the chip, or even sorry, half of the array, or even the full array. And so the paper has been recently submitted to the archive as of last month. Please scan the QR code if you are interested. I'm also happy to drop the link if you just send me a message on Slack or an email. There will be a data release that soon follows, which consists of 44 noiseless position angles plus analogous dithers. And there's a lot of great work on the way in the future that we'll be talking about within the rest of this data challenge and the other ones to come. And so just as a quick summary, we have produced a realistic Roman extragalactic Grism scene. We have source injection capabilities where we can add custom sources of your choosing. And we have a methods paper that has been submitted and an upcoming data release. So thank you. Take questions.
You mentioned that you developed the tool primarily for extragalactic simulations, right? But there is a kind of a discussion that maybe even the galactic plane could use the slitless mode. So it sounds like your code would also work for maybe probably simpler scenes, right? You just need an image of the galactic plane, then you can choose if you inject stars, galaxies, or whatever you want.
Yes. We specifically, as extragalactic folks were specifically interested in developing it for the extragalactic scene, for developing live and alpha, related simulations. But yes, we can use any image as long as it comes with an SCD library and a segmentation map. So thus we can then do stuff with like the galactic plane and see how crowded like all those foreground stars would be. And thus, can you actually then give this resulting scene to someone else who has spectral reduction code to then see, can you recover all those stars? Yeah.
Hi there. So the source injection is really interesting. You said you can use really any image. You've used HST a lot in this talk. Is there a preferred survey that the images should come from to match the resolution? Is it really just any image in the right wavelengths?
Yeah, it could be. It's preferably an image that's in like the near infrared, right? So that way, morphologically speaking, it's matching what you'd expect out of Roman. But as long as there's an SED that spans 1 to 1.93 microns and you have your stamp, you can put it in and it should be good for you to be like, okay, how does this now appear in the scene? And thus, what can we then extract information from it? Yeah.
So you mentioned the data release with the 9 detectors. Is there an idea that in the future that you'll release something with all of the detectors and possibly just, less position angles?
Yeah, that's something that we're considering for the future. There's ongoing deep near infrared imaging going on through JWST, for example, that does cover a larger area that we can thus use as input and thus maybe get like half a detector array, if not a full one, just with less position angles. So then that way we could say, this is a full scene. What can we do with just one pointing, for example?
What's your timeline for adding noise?
So we do add noise. I think I brushed over this, is that we just do a simple Poisson noise model with some exposure time. Yeah. Oh yeah, so we will, yeah, that's a caveat, is that we can also be releasing ones with noise, right? But our pipeline does have the ability to thus add noise because you'd want to co-add your injected image to the noiseless image and then add noise to that after that.
It is. The reason noise is added stuff. The reason noise is added in the end is because that way you don't have to do it twice for two different exposure times. So you have the realistic scene and then you add the sky noise according to your exposure time, the computational setting. Okay.
This is really cool. Thank you so much. Are there any plans to add detector features to this, start from a more realistic like scene?
Yeah, there are plans. And we will be working on it as we iterate through the rest of this data challenge. Okay. In this case, I will then return this to James, who will be now talking about Roman and the Prism capabilities. Thank you.
Okay. Thanks, everybody. Hopefully this will full screen in a moment. So I'm here to speak right now about the Roman Prism. This is going to be a somewhat qualitative introduction to Prism data. And the reason for that is that Trias Strasmadia is our team's sort of Prism lead, and he had to leave the US for some family issues and isn't back yet. And we decided that the sensible thing to do was to talk about the Prism here, but for today's version of the data challenge and working with sample 1D spectra that will follow my portion of this, we will be focused on the Grism primarily. I'm hoping that we can add some Prism stuff midway between now and the summer AAS, but the target I'll sign up to is the summer AAS. So I also wanted to acknowledge Sangeeta for making the modified Pink Floyd diagram on the right. But so I wanted to begin with a short history of the Prism, partly because for at least 3 of us in the room, this was the summer of 2018 or a chunk of it. There was, a core objective of Roman is to study dark energy, and that is broken into the 3 different methods for studying dark energy. Baryon acoustic oscillations, which of course is a science motivation for having the Grism on the spacecraft. And then supernovae is the motivation for having the Prism. When you're trying to understand supernovae, spectra are a very helpful tool. And what you're looking for a redshift 1 supernova is a very faint point source in the infrared. And this is a great use case for slitless spectroscopy from space. You get up to space, you have the diffraction limited performance or nearly so of a 2.4 meter telescope in space. That gives you a much higher signal to noise for a point source. You get above the atmosphere, that gives you much higher signal to noise throughout the near infrared because you're not fighting either H2O absorption or the OH emission forest. So this is, and then what kind of slitless element do you want? Well, supernova ejector have, typical speeds in the thousands of kilometers per second. And that means their spectral features are broad, right? They're Doppler broadened. So the optimum resolving power of your spectral element should be comparable to C over a few thousand kilometers a second, which is about 100. So that's what the Prism is designed to do. It gives you resolving power lambda over delta lambda in the range of 100. And this was added in 2018. It replaced an earlier idea of having an integral field channel on the instrument, which basically was ended up being a little too expensive to do. But the Prism lets you do multiplexing. Instead of hitting one object at a time, you get several supernovae at a time. And that led to, an affordable way to keep spectroscopy for supernovae on the Space Telescope. Okay. And how do you build this Prism? Well, you need to disperse the light without bending it when you add a Prism to the Roman design. That's because you already had a camera being designed for direct imaging through a filter. So the light comes in one side, it goes through the filter, the light you want goes straight through to your detector. If you put a simple wedge prism in there, you're bending the light and you get a beautiful spectrum, but it's not on the detector, it's somewhere else. So that's a problem. So instead, what the Roman prism does is it has two different wedged elements with opposite wedges, so that on average, the central wavelength is going straight through. The red light is bent a bit one way, the blue light is bent a bit the other way. And there were somewhat heroic efforts both to design this and to build it, because it turns out one of the glasses you need is really rather fussy to work with, calcium fluoride. But this was done, and this is the performance of the resulting element. I think this is a design plot, but the realized performance is basically as designed. This is showing the spectral sampling as a function of wavelength, or the lambda over delta lambda resolution as a function of wavelength. And the point this is making in a sort of theoretical way is that the resolution of this prism varies from the blue end to the red end. So at the blue end, the resolving power is up here at lambda over delta lambda near 200. Across the middle of it, it's 100 or a touch below. So, and then in terms of, angstroms per pixel, that starts out at 20 and tops out around 90 angstroms per pixel. And remember, slitless spectroscopy, the actual resolution you have on an object is dependent on the size of the object. If your object is a point source, it's basically about 2 pixels. So you take that spectral sampling and double it to get the approximate point source resolution. For the prism, because of the optical design challenges, we're a little shy of diffraction limited at some places in the field, but it's pretty close to that. And I want to now walk through a little of what this actually gives you. So these plots are a little bit old, pulled off my disk, but the first one on the left that I want to show is what happens if you take a comb spectrum and run it through this prism. And it's a nice sort of qualitative illustration. You won't see this source in the sky, but this has a delta function emission line every 100 nanometers of wavelength, and they're all the same flux. And what you're seeing here is that the lines are narrow and therefore have a higher peak at the blue end. And as you go to the red, they're getting broader and broader, and therefore, you're just spreading the light over more wavelength, the peak is dropping. Over here on the right, this is an illustration applied to a green pea galaxy, a very strong emission line source, one of my favorite object classes. And you'll be seeing more of these later in the session. But you can see a set of strong emission lines. The bottom is an input spectrum at Sloan sorts of resolution, so R of a couple thousand down here. And you can see this forest of strong emission lines. This is what you would, at the top panel, is counts versus pixels that you would get in the prism. So you can see that this cluster of lines at the, in the blue 1/4 of this plot is spread out over the almost half of this plot in pixel space. You can see also that this oxygen 3 doublet is merged together here into a single feature that you can't pull apart at the prism resolution. The Grism would get that, by the way. And this is basically taking this spectrum, but putting it back into F lambda versus wavelength. So in this picture, the bin sizes are changing as you go from the blue end with small bins to the red end with wide bins. And if you pay close attention, the peak heights in counts and the peak heights in F lambda have, the dependence you would expect for the bin size changing as you go. Okay, so that's one kind of galaxy. Here's a couple different galaxies. On the left, we have an elliptical galaxy at redshift of 2. So that's the 4,000 angstrom break. And on the right, we have a galaxy with some lines and some continuum. I want to keep moving. These are now plots that Tree produced rather than plots I made. So they, I think, have a more faithful treatment of a number of instrument issues. This is closer to a full simulation followed by a full extraction of the spectrum. Mine were basically 1D transformations accounting for the resolution as a function of wavelength. And I've picked a handful of things out of a larger number that Tree gave us. And this one I picked, it's a hot star. You can see, I'm guessing an A-type star from the forest of hydrogen absorption lines that you see in the input spectrum, which is black. And the green is the output spectrum. And you can see that over here on the red end, those absorption lines have kind of gone away. You just don't have the resolution to pull them out. Here at the blue end with sufficient signal to noise, which I think is effectively, near infinity for a bright star in this plot, you do still see them, although they are much diluted relative to the input. And on the right is a supernova spectrum because, we should have some in this presentation. Tree would have more if he were here. And then I just wanted to go through a few slides that also show a bit more of the supernova application. I got these from Sangeeta, who got them from, I think, Tree many years back. So they are probably, with my apologies, not the latest that the supernova group could produce, but this is their simulation flow for, postage stampy supernova at a time with a host galaxy. So we have two input spectra here. The red is a host galaxy. The black is a supernova. The y-axis units are different, but even though the galaxy has more flux in total, the supernova flux is all concentrated to one point, which will make it stand out in the coming spectra. They take a scene, convolve it with a realistic PSF, and that's your output scene at one wavelength. And then they have done a whole bunch of different redshifts. So these are different scenarios, redshifts and different locations, I think it's just angular diameter distance coming in. The supernova is farther from the host in angular distance at low redshift. And then these are some of the output spectra with background light added in. So you can see that these are 2D spectra. You can see the sort of lumpy supernova spectrum most clearly at the high signal to noise, low redshift case. As you go out to the higher redshifts, the thing is just getting fainter. So the plot is looking more and more like, the noise is dominating, but there is still interesting signal to pull out. These are 1D extractions along the trace of the supernova. And again, you can see very high signal to noise in the nearby ones and signal to noise dropping as you go out. And finally, here's a montage from Rubin et al. 2022 showing noiseless and 1 hour's worth of simulated data for supernovae. This is a single supernova, at redshift of 1, but it's about 25 different times in the life of that supernova. So you can see at redshift 1, near peak light, you're getting, interesting signal to noise on a single hour exposure, and you're still getting, if you combine a few of these at late time, you're getting interesting information on the late time. So I'll pause there and see if there are any questions. Rebecca.
So in your expert opinion, what are the minimum number of roll angles or angles that you would need for a good clean subtraction of a host galaxy?
Okay. I think.
I know it's a loaded question, but I wanted your opinion.
Yeah. Well, I'm actually going to defer it to Isaac, who's already holding a mic. My read on my summary of what he's told me in the past is that you're getting into the game with something like 10 and you're doing really nicely with something upwards of 20, but I'll let Isaac correct me if I've got that wrong.
Yeah, I think it would depend. Yeah, so how bright is the supernova? How bright is the relative to the host galaxy? I think that it would be interesting to actually inject these into an extragalactic field and see what we can extract from it with our simulations. Yeah.
Isaac is our team pessimist. Let me be. Yeah, so let me be a bit more optimistic. You have two things going for you in supernovae. One, your supernova is a point source. Okay, so you know where it is exactly. These are for things that you don't know they're even there. Okay, sorry, Isaac. And two, you have a time-dependent thing. So at some point, hopefully, your supernova will go away. Otherwise, it's not a supernova. So you have a clean subtraction.
Okay, let's keep the discussion coming for 1 minute because what I need to do now is find the Jupyter notebook window, and then I'll hand it over to Sangeeta Kumar and Menak Singha to walk through our Jupyter notebook. But I have to remember which tab it is on, and that is a slow process for me. I might actually unplug from the projector for 1 minute while I do that, so you don't have to see all of my chaos. So yes, there's a Git repository that Sangeeta has put up, and the notebook is online. So for people who don't want to join that walkthrough, I guess this is a moment of break, but we hope we will still have it. Yeah, okay. All right, very good. And we are recording the session. I have an intention of getting that up on YouTube at some point. I'm not going to promise that it'll be this week in the middle of all of the conference, but before too long. Yeah, okay, I will do that, but I need to actually make sure I have it myself. Okay, I think I have found I've found the notebook. Now I'm going to put the how to find it yourself on the screen for a minute, and then I'll hand it off. And Sangeeta, you're first, is that right? Yeah, okay. And we are at okay, we've got 30 minutes. I'm afraid that's right on schedule, right? We had 20 minutes book kept for this. So suggestion, yes, I see someone's ahead of me. If you can snapshot that on your phone, then I can flip over to actually showing the data challenge screen. If you signed up on our Google form, you should also have this in an email. I pretty literally cut and pasted this slide into an email last night just before bed. But all right, I'm not seeing more cell phones raised, so I will exit this and see if I have lost the screen yet or not. I think it's okay. And if you want, I want to figure out how to full screen this thing is all. Is that full screen? Enter full screen. Okay, yay. And if you need to zoom it anymore, Apple Plus is pretty reasonable. Apple minus if you need to unzoom it, but this looks like it's
Okay, yeah, I think
a
that's
good
perfect.
size. Okay.
Yeah. Okay.
Thank you.
Thank you, James. Hi, my name is Sangeeta. I will be walking you through the Jupyter Notebook for the data challenge. I just want to go through this flow chart, which just describes how this Jupyter Notebook will be run. So first we have our template spectrum, which is at its rest wavelength. And this is a spectrum from SDSS. It's a galaxy. And from there, we will be redshifting it. And then from that redshifted spectrum, we will be degrading it to Grism resolution. And That output spectrum will then be used for emission line fitting, where we can then estimate the redshift. That portion will be done by Manik Singha. But I'll just be walking you through the portion where we'll be degrading a spectrum to Grism resolution. So first, I just have here some functions. This one, just d redshifts and redshifts of spectra, so that you can just input any spectra that you have with a known redshift, and then you can redshift it to whichever redshift you want. Pretty straightforward. And then we have this Roman Grism resolution function, which will broaden and smooth a spectrum to a Grism resolution. And so here we're just loading in the spectrum, we're getting the wavelength, and we're getting the flux. And again, this is just a rest wavelength. So here we have a rest frame wavelength spectrum, and then we redshifted it to 1.6. And that's what that looks like. And again, like, because this is at Grism resolution, we have it from 1 to 1.93 microns. So here's where we have degraded the Roman, the spectrum to Grism resolution. And we have this parameter here that is used to for the size of the object. So here is a plot of what each of what each step in that degradation looks like. So here we have the original in blue, and so in this top plot here you can see that the amplitude goes down. In the red we have the first smoothing that happens, and then in the green, or in the black, we have the second smoothing. And then in the green is the final resolution, which was just after resampling. So we have these two lines here that were here. This is like H alpha, and then we have H beta and O3. So you can see that the amplitude decreases, but there's also line broadening occurring, both in these two spectral features. So that was basically how we degraded the spectra and how it looks like after each smoothing function within the function that we used. So this next part will be done by Manik, where we're going to be fitting an H alpha line to this spectra.
Thanks, Sangeeta. So in this portion of the data challenge, we'll be actually focusing on the H alpha line fitting for number one, estimate the redshift, and then two, estimate the flux. Because when we actually do science with Roman, one of the most important things is you getting a distant object. What's the redshift? How far is it away from us? And what's the flux? What's the luminosity? You need all these parameters to do important science. And that's what Roman's been built for. So once we actually have a Roman spectra, in this step, we'll be having like a gentle introduction to how to like walk you through and to actually use the Roman spectra to do science. So for in astronomy emission lines, we typically consider them or approximate them to be Gaussians, although they're not really Gaussians, but that's the best way to make our life easier, right? So when we have like a H alpha spectra, like just Sangeeta showing us before, so look into this, a simple Gaussian may be a fairly decent approximation. And for the wavelength fitting purpose, we don't go too far because you have a noisy spectra and you go really too far, then the noise starts to really affect your fitting and then your fit doesn't converge. So what we do is when we see a emission-like feature, we basically stick like very close to it and make sure our fitting range doesn't go too far. And that's all these are to like make our life easier and make the fitting step as smooth as possible. So now we're defining a Gaussian functions that your typical like amplitude time, like an exponential Gaussian functions, and then we add like a continuum. And what's this continuum for? For example, for galaxies, you have like a host galaxies continuum, and for quasars, you have an Aegean continuum. Again, just remember that we're not using those slopes because those are for like a much larger wavelength range, and this is for much smaller wavelength range. So we don't need to make things complicated. Just keep things simple. And here we are just defining all this parameter, like all these means, because for the people who are very new to this, like amplitude is basically
line peak amplitude, and the mean is your central wavelength. Sigma is your line dispersion, and you have the continuum. And then all these are used to estimate the flux. That's a very important parameter because basically then we're going to use that to estimate luminosity. And when you have a Gaussian's amplitude and width, you can very easily use those two parameters using these functions to estimate the flux. And that's very simple. And that's what we're going to be doing in this tutorial. So let's do this. We want to read the data from a Raman spectra first. So in the 0th column, we have the first column, we have the Raman wave or the wavelength. That's in angstrom. And then in the second column, if you read that, that'll be in the flux. We call it flux, but it's actually flux density. Now, one thing to note that these are in the units of 10 to the minus 18 ergs per centimeter square per second per angstrom. So if you want to do fitting with that that small values, your fit will go absolutely crazy. So to make our life not so crazy, we simply multiply that with that exponential like 10 to the 18 to make things like a bit more standard units. And the same goes for the flux error, the flux density error. So they're also in the units of 10 to the minus 18 ergs per centimeter square per second per angstrom. And we're just going to make them in standard units. And we want to fit we want to see how the spectra looks like one for H alpha. So this is how the Grism resolution H alpha looks like. It's like not so nice as your regular SDSS spectrum, but like that's what we're gonna be getting from Raman, and we'll be using it and do some great science. So going forward, what we want to do, we just plotted this wavelength to like make sure the H alpha line pops out. And as I mentioned before, we all just want to stick to this wavelength range so that we don't have to go to many complicated fit and like strong, really weird continuum shape. So we are masking everything out outside of like a 16,900 on the blue side and 17,200 angstrom on the red side. So now we mask the data. Now we have to do some initial guess, like what are the initial guess? So for example, I was talking to you about like the amplitude, line center, line width, and the continuum. So look here. So you have it starts from 2, the base, and then it goes up to 12, right? So the difference is like 12 minus 2, 10. So we take like 10 as the amplitude guess. And now for the line center, this is between like 17,050 and 17,100. I was like, say 17,075, like a mean value between 50 and 100. So that was my guess for the line center. Line width could be a little trickier. So it doesn't look like a very broad line. So I don't think it will be like a 50 angstrom or something, because like it starts from 50, it's like 100. And we're talking about dispersion, right? So it shouldn't be like a 50 angstrom. It should be like much smaller, like 50 by 3, like a 16. So I say 15 angstrom. And then for the base, it is 2, sometimes drops to like 0. So I say, well, 2 plus 0 divided by 2, 1, like a very reasonable guess, just to make sure the fit goes right. And let's see how things go. So here I just basically tell you the same thing. These are like we're giving out the best possible approximation just to make sure the fit converges, because we're dealing with noisy spectra. And one more thing when you deal with noisy spectra is put realistic bounds, because you don't want your amplitude to be emission line amplitude to be negative. That's unphysical. That's going to make your life much worse. And then when you see emission line centering around like 17,070 or 75 angstrom, you are sure that like that won't, the emission when you're fitting it, that shouldn't shift between like, somewhere really crazy, like 16,900, 17,200. So we are putting bounds on the line center. And these two are the most important parameters from my spectroscopic fitting experience. Like once you have your line center and line amplitudes properly in place, you will be fine. So that's what we're just trying to do, to make sure the fit behaves like pretty well. And saying the bounce is like 1 and it goes to 100. I mean, obviously you see that the line dispersion would be like 100, but still like it's just giving you like some kind of sensible value, because you don't know like how the fit will be, so that at least the fit has like some kind of good enough parameter space to work on, and that actually can give you some realistic chi-square values. And then, yeah, and for the continuum, it's 0, the less value, because obviously we don't see a negative continuum here. And infinity, because just for like flexibility, so that the fit can also again work on like some kind of flexible parameter space. So we use the SciPy optimized curve fit that is like a least square algorithm to fit all the spectra. So we use this Gaussian function. We masked out all the anything beyond 17,000, 16,900 and 17,200. We take the plus density and the error values, put the bounds on, and then we just do our fit. So from the fit, what we would get? All this amplitude, the line center, line width, and the continuum. And then we use the amplitude and the line width to estimate the parameters. Like we do it all at once, and then we see the results. So first I want to show you like how the fit works. So the fit looks beautiful to me, at least, because I'm kind of biased. So when you do like a Gaussian fit, the fact that we give so much sensible guesses, that's why we're seeing like this, even to like a noisy spectrum like this, like we're seeing such a like a nice fit to the emission line. And that means that it worked. So now going up, what things looks like. So we have like a 10 to the 18 minus 18 units, we put them back. So the amplitude is 10 to the minus 17 or centimeters per second per angstrom. But this is the key part, the central wavelength, 17,066. We guessed like 17,075, like it's like very close. Like the fact that we give such a sensible guess, that's why we're seeing like such a good fit, and it's like coming up very close. And look at this, like the line width, we put like a 15, it's like 13.64. So it was almost absolutely like we're very, very close, like how we put the initial guesses. And the continuum was much smaller than the amplitude. You see like about like 6 times smaller, and that's what we saw in the figure, that like the continuum is like almost like 6 times smaller than the line flux, and that's that peak, and that's what we're seeing here. And finally, we use all these numbers to get the line flux, which is like 3.5 times 10 to the minus 16 hours per centimeters per second. And this is a green pea galaxy, like one of the strong emission line galaxies that resembles that dwarf galaxies at the cosmic dawn. But these are like the local analogs of those cosmic dawn galaxies. Now, when we redshift them with Roman and put them at like a much higher redshift, this is how Roman will see those galaxies. And that will be like, would be one of the most important science Roman could do. So all these values right now, without their uncertainties, doesn't make much sense, right? So one of the most important things we want to do is to estimate the uncertainties, to get their redshift and get their uncertainties. So before we go to that, we need to do a little bit of our error estimation. And how do we do it? It's called a Monte Carlo simulation. So we create an empty list on the amplitude, the mean, and the sigma, and the all the continuum and the fluxes. And then we simply add noise and do it the process 100 times. So what we do, we just add random noise and we feed the data 100 times, and then we store the values in a list and we take the standard deviation, and that's basically give us all the uncertainties. So let us see how the uncertainties look here. So the amplitude is like 10.2, 0.7, like a very low error. The central wavelength, which is the most important, but 17,766, is almost just like a less than shy, but like a 1 angstrom error. So like you see like how precisely we estimated the error. And the same goes for the line dispersion, like 13 plus minus 1 angstrom. And the line flux, like it's about like, it's over at least a 10 sigma detection. The H alpha, one of the brightest mission lines, Romans detecting at over like 10 sigma confidence. Like that's where you see such a bright mission line feature picking up. So we know that the H alpha's rest frame wavelength is 6562.8 angstrom. And now we know what's their observed wavelength, which is 17,066. So from that, we can estimate our redshift, which is basically you subtract the rest frame wavelength from the observed wavelength and then divide that value with the rest frame wavelength. And how much we get? The rest frame wavelength is 1.6, and the uncertainty, which will be basically the error in the central wavelength divided by the error, but divided by the central wavelength, which is like 5.5 times 10 to the minus 5. So we are getting the redshift uncertainty in the order of 10 to the minus 5. Like this is like how precisely we're estimating the error. And that's what Roman's capable of. So now this is just like a small exercise, and we have many sources for you to try on. So if you want to give it a shot, we have like 5 galaxies, green pea galaxies, and each of these spectra are like listed here. You are feel free to like try it on your own and tell us what the redshifts are, and yeah, or just find it out yourself. So yeah, please let us know if you have any questions. And that's all for me.
Any questions on the Jupyter notebook walkthrough that I'd like to go with a couple of closing remarks? Are there questions for either Nina or Mark? So open the floor to more general questions about any part of the lecture, and talk about directions forward after that. So this putting this data challenge together has also been a learning experience in Python for me. So I wanted to acknowledge our more experienced programming teammates for bringing me along for the ride, but it's been fun. And I think I can do it. So I think anyone else can too. Question. Yeah, do we have a mic to? Yeah. Okay, I can pass it along.
So slow question to the data challenge. So is the so I know at least for the spectral extraction, there were a couple of softwares listed. I know at least a few efforts in trying to get the Grism simulations as well. So is the general idea that there would also be like a centralized data challenge where we can compare and contrast different simulations, different extraction code, and how large is this eventually going to grow?
Okay, that's a great question. I'm going to pull Sangeeta Malhotra's slide back up, I think, because that's got our overview of the data challenge process. So I'm actually gonna hack up a copy of this slide. So you are here today, and where we are going is, this data challenge. In some sense, the core of the data challenge is simulated spectra with the Grism properties, right? The resolution and a noise level that's a reasonable, they're like the high latitude wide area survey in terms of the noise level. And right now they are emission line galaxies. I am hopeful that we can add some other kinds of objects into there before long. And for analyzing them, the Jupyter Notebook is a tool that we could put together that anyone who hasn't got another favorite tool already can use. But if you do have another favorite tool, by all means, jump in, use that. The form of the challenge itself is basically find the redshifts of these objects, measure the line fluxes. For the objects we've been looking at, you've seen, you clearly want an H alpha line flux, the oxygen 3 doublet H beta. and there's some other lines you might want to go after, depending on which of the spectra you pick up. Some of those are more clear, some of them are less clear. And with the noise level added, you're probably not going to be getting a lot of the fainter lines at the simulated depth, but part of the challenge is see how far down into the noises you can push with that. Then the second step of the data challenge, which we plan to have around the summer AAS, is going to be 2D spectra where you can do the extraction as well as the 1D fitting. So, at some level, we're scaffolding this by building up from the things that take smaller and easier tools to the things that take larger and more complicated tools. And we also hope to add the Prism in at this point. It was initially hoped to have some 1D Prism spectra in here, but I hope to have them in at Challenge 2. And let me just add a text box and write down here the other thing that I wanted to say, which is that we have an email address, which is it's SPQR, which is the acronym of our Wide Field Preparatory Science Program, DC for this location, and 332 because apparently spqrdc@gmail.com already existed. So, so there we are. It is not the most memorable email address, but you may have it in your inbox already. And what we can do is if you email questions about the data challenge, anything from I'm having trouble downloading it to cell 17 isn't working to this is great, but is that really a spectral line at this wavelength? We can get back to you on email or set up a Zoom call with a member of the team. So the intention is to support this data challenge over the coming few weeks. We didn't actually, did we decide a sort of when we want people to aim for redshifts and line fluxes? We haven't decided a sort of a nominal time scale, but we're discussing that we can, at the end of the the 3-step process, we are hoping we will have a journal paper describing the data challenge, and people who participate in it could join that paper. So that's an end goal, one of the end goals of the challenge. The real end goal of the challenge is to help develop a Roman spectroscopy community, whatever your science interests are, anything from, galactic plane to epoch of reionization. We are interested in trying to help support all of it. And I think the questions about whether we can simulate something like a bulge field, those are good for a splinter discussion sometime during this meeting. I think in principle we should. My only questions are computational resource related, but Sangeeta has something more cogent to say, I think.
I'm wondering if there's enough demand to go straight to challenge 3 and you want your field so that you can get on with doing the real stuff. And you don't need all of this build up. If there's enough demand for that, we could just do it. Let us know.
Okay, so
You're absolutely free to use whatever tools you want to. Right. And actually the real value of this comes from people using different tools, so we can have a sort of comparison of how well different tools do. We just didn't want to scare the newcomers.
okay. I'm just seeing if I had anything else I wanted to. Yeah, I think that's covered what I wanted to say. Thanks to everyone for attending. Sangeeta, do you have any other closing thoughts? Okay, are there any other questions? All right, I think I'm gonna, if you want to find Sangeeta Malhotra or me, she's at the Roman booth today, 3 to 6:30. I'm there, I want to say tomorrow afternoon. And we'll be around the meeting. Shoot us an email, and hey, take 5 minutes back to actually breathe and see someplace outside this room before your next talk. Thank you so much, everybody.